For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. Problem F.1. In this problem, we will investigate ML decoding using the standard VA on a minimal conventional trellis, or using a modified VA on a tail-biting trellis. Consider the 6-3-3 binary linear code C that is generated by the following generator matrix. A. Find the state and branch complexity profiles of an unsectionalized minimal trellis for C. Draw the corresponding minimal trellis for C, and label each branch with the corresponding output symbol. Verify that there is a one-to-one map between the codewords of C and the paths through the trellis. Solution. We first find a trellis-oriented generator matrix for C. Replacing the third generator by the sum of the first and third generator, we arrive at the following generator matrix. livexamhelper.com. Since the starting times and ending times of all generators are distinct, G0 is trellis-oriented. Using the active intervals of the generators in G0, we find that the state dimension profile of a minimal trellis for C is 0, 1, 2, 2, 2, 1, 0, and the branch dimension profile is 1, 2, 3, 2, 2, 1. Explicitly, a minimal trellis is. We verify that there are 8 paths through the trellis corresponding to the codewords 000000, 111000, 001110, 110110, 011011, 100011, 010101, 1011. B. Show that the following unsectionalized two-state tail-biting trellis, TBT, realizes C. Recall that in a TBT there may be more than one state in sigma 0 equals sigma 6, the starting and ending state space, and that the valid paths are those that start and end in the same state in sigma 0 equals sigma 6. Verify that there is a one-to-one map between the codewords of C and the valid paths through the tail-biting trellis. livexamhelper.com. Solution. Here the two states at state time 6 should be regarded as the same as the two states at state time 0. The valid paths are those that start and end in state 0, corresponding to the four codewords 000000, 111000, 001110, 110110, and those that start and end in state 1, corresponding to the four codewords 011011, 100011, 010101, 100, and 1101. Thus we verify that this TBT realizes C. Draw a normal graph of this tail-biting trellis realization of C. The normal graph of a tail-biting trellis looks the same as that of a conventional trellis, except that the two ends are joined so that the ending state variable is the same as the starting state variable. In this case, all states are binary, and the constraints are alternately single parity check and repetition constraints. So the normal graph looks like this. livexamhelper.com. Note that G is a TBT-oriented generator matrix for C, in the following sense. If the active intervals of the generators in G are viewed on an end-around basis, i.e., 0, 2, 2, 4, and 4, 0, then there is only one generator active at each state time, so the corresponding state dimension profile is 1, 1, 1, 1, 1, 1. Similarly, these end-around activity intervals imply a branch dimension profile of 2, 1, 2, 1, 2, 1. The TBT above is generated by these three end-around generators in the same way as a conventional trellis is generated by conventional trellis-oriented generators. C. propose a modification to the Viterbi algorithm that finds the maximum likelihood ML codeword in C using the tail-biting trellis of part B. Compare the complexity of your modified VA to that of the standard VA operating on the minimal conventional trellis of part A. Solution. We can run the standard Viterbi algorithm on the two sub-trellises consisting of the subsets of valid paths that start and end in states 0 and 1, respectively. This will find the ML codeword among the two corresponding subsets of 4 codewords. We can then choose the best of these two survivors as the ML codeword. LiveExamHelper.com. Roughly, this requires running the VA twice on two two-state trellises, compared to one four-state trellis, so in terms of state complexity the complexity is roughly the same. The maximum branch complexity of the two-state trellises is 4, whereas that of the four-state trellis is 8, so again the branch complexity is roughly the same. Finally, if we do a detailed count of additions and comparisons, we find that both methods require 22 additions and 7 comparisons, exactly the same. We conclude that the simpler tail-biting trellis requires the same number of operations for ML decoding, if we use this modified VA. D. For a general N-K linear code C with a given coordinate ordering, is it possible to find a minimal unsectionalized tail-biting trellis that simultaneously minimizes the complexity of each of the n-state spaces over all tail-biting trellises? Explain. Solution. The example above shows that this is not possible. The conventional trellis for C is also a tail-biting trellis for C with a state space sigma 0 equals sigma 6 equals 0 of size 1. Thus, as a TBT, the conventional trellis minimizes the state space size at state time 0, but at the cost of state spaces larger than 2 at other times. We have already noted that it is not possible to construct a TBT for C that achieves the state space dimension profile 0, 1, 1, 1, 1, 1, which is what would be necessary to achieve the minima of these two profiles simultaneously at all state times. LiveExamHelper.com. Moreover, we can similarly obtain a tail-biting trellis with a state space of size 1 at any state time, by cyclically shifting the generators in order to construct a minimal conventional trellis that starts and ends at that state time. But there is obviously no way to obtain a minimal state space size of 1 at all state times simultaneously. E. Given a general linear code C and an unsectionalized tail-biting trellis for C, propose a modified VA that performs ML decoding of C using the tail-biting trellis. In view of the cut set bound, is it possible to achieve a significant complexity reduction over the standard VA by using such a modified VA? Solution. In general, we can run the standard VA on the sigma 0 subtrellises consisting of the subsets of valid paths that start and end in each state in sigma 0. This will find the ML codeword among each of the sigma 0 corresponding codeword subsets. We can then choose the best of these sigma 0 survivors as the ML codeword. The complexity of this modified VA is of the order of sigma 0 times the complexity of VA decoding a subset trellis. The subset trellis state complexity is the state complexity max. For a conventional trellis for the code C0 that is generated by the generators of LiveExamHelper.com. The TBT-oriented generator matrix for C that do not span state time 0. Choose a cut set consisting of state time 0 and state time k for any other k, 0k less than n. By the cut set bound, the total number of generators that span state time either 0 or k is not less than the minimal total number of generators that span state time k in a conventional trellis for C. Therefore, for any k, 0k less than n. But this implies that max. Thus no reduction